slides. So yeah, I'm going to present this paper. It was a spotlight paper at ICLR last year or this year on critically damped score-based generative modeling, basically. So critically damped Langevin diffusion for score-based generative modeling. So yeah, the links are all here. I'm going to share this in the Slack or email. So it's only a simple Google slides, so nothing too fancy. Okay. So just through the motivation of why this is interesting work. So ignore everything for now, apart from the this smooth diffusion block here. So you may have seen previous score-based generative modeling plots where the trajectory is very noisy, like this V, for example, this PV to PV1. A typical SDE is quite noisy. In this proposed method that I'm going to go into, the diffusion and the data space X0 is quite smooth using this damped forward noising process, essentially. Why is this interesting, or why is this useful? It means the network to learn the score network can be smaller and simpler, so a lot smaller for high performance, and also a bit more stable for training. Okay, so that's the overall gist of the thing. This won't make a lot of sense right now, but I'm going to go into it a bit more detail, and then it'll hopefully make sense afterwards. Okay, so as a recap, you've seen all this. Most people here have seen all this a few times now. Score-based generative modeling, essentially you take data, you would apply noise to it through a form of an SDE. So the forward noising process, this forward SDE, and typically to generate new data, you learn this score term using a neural network, simulate your final your terminal or your prior sample. So your start of the data X0, you apply some SDE, which converges to some data distribution called a prior, simply a Gaussian noise. And then to sample new data, you simulate this SDE starting from your Gaussian prior to generate new data again. So this is the form for any SDE, given the right conditions that such reverse diffusion exists. It has this complicated score term, which is the gradient of the log density of the noise data. And then, yeah, typically one learns this using a network. Here, denote the network S theta. So yeah, typical, very standard score-based generative modeling. This is the objective that people typically use. Okay. And so, yeah, so in a typical SGM, the data, I guess this is the reverse process. It's typically quite noisy. So it's yeah, it's not very smooth basically. And this means typically the networks used to learn this drift or the score term are very, very large, like hundreds of millions of parameters. I think the current state of the art is like 500 million parameters. So it's not a language model, but it's still like you can't really do that on a single GPU. Okay. So what's the innovation in this paper? So rather than using a forward noising process like an Ornstein-Uhlenbeck process or a Gatt or Brownian motion, which is very simple, you augment the state space. So rather than adding noise to xt directly, augment the space. So from xt to ut, where ut has the xt plus some velocity term, and then noise is added. I think they call it injected in the paper into the data through the velocity term. So this is essentially your drift is this f, and your the variance associated is this g. So recall this. Here we have f and g. Replace this with these terms here. So
what is the critically damped refer to?
Good question. So I'll go into that in a second. So I don't know an awful lot about this whole damped, overdamped, underdamped stuff. The link that they share in the paper links to this book, which is not available even on Sci-Hub, which is so it makes me wonder whether it even exists. But yeah, okay. So this is the SG essentially. So what's the benefit of this? One, because you're not adding noise to the data directly, the data trajectory is smoother. And I guess it's quite well known in Monte Carlo, I suppose. So if you replace actually this term here, no one can see it on the slide, this negative x I guess this can be, if this is, as long as this is a linear term, I guess this can be sampled in closed form as a nice solution and things. If this was like a more complicated tonal distribution, then this would be, you wouldn't be able to sample this in closed form, I guess. Okay, so here the parameters that are in question are this gamma, which is like a friction term, this m, which is a mass term, and the beta, which, so typically beta is like a step size. Essentially, you embed the step size into the SDE itself. So this is a fixed beta, but typically people use a beta with like indexed by time, so a non-homogeneous beta. Okay, so this is embarrassing, just copied and pasted from the paper. But essentially, how do you find, you can sample from this SDE in closed form by sampling your data and then applying, essentially you have it'll be a Gaussian distributed given condition on the data, and you'll have the mean and variance are given as follows. And the limit is very standard. So like I said before, in the noising process, when you go from data to a simple prior, you want the prior to be sampleable. So you want to be able to sample from this prior and in an easy way. So it has a nice closed form or simple prior. And if people are interested, the way you prove that the closed form solution for sampling from the noisy SDE is essentially using this work from Simosaka and people. They create an ODE for the parameters of your of the noise distribution, if you like, so the mean and variance, which forms an ODE, and then solve this. So I thought that was interesting. This is used quite heavily in score-based generative modeling. So in the SON papers and things, everyone uses this kind of proof. There are easier ways, but this is the most general. Okay, and so what does it mean by critically damped? So yeah, essentially, the motivation for this was that when you have this term here, this gamma squared term, if this is equal to 4m, the mass, this is what they call critically damped. I don't think this is a standard term. I think this is a term they introduced. But this was in this physics paper. I forgot to put the link. It's what's it called? McCall, Classical Mechanics from Newton to Einstein. I'll put the reference in. Essentially, their motivation was saying that if you at this rate, you have it mixes fast. Basically, it has. They say it's somehow optimal in terms of mixing, but it doesn't. It's not very precise in the definition here. But essentially, when you have underdamped, as shown in this point here on the screen, in diagram A, where your gamma is fixed at the 0.1 of the critical gamma, you have some oscillatory behavior. So this will be, I guess this will cause slow mix. It will be very smooth, but it will be slow to mix because essentially you're exploring quite heavily and not progressing in the actual diffusion. And similarly, when it's when the gamma or the friction term is very high, you have a very noisy trajectory. So in this case here, in diagram C and D, for example. So this is typically what you'd see in an SDE, in a standard SDE, I suppose. Okay, so and then somehow your the critical gamma gives you a nice sweet spot between actually progressing in the SDE, as in moving forward in the SDE, as well as being smooth. So that's the idea. Okay, so this is all, and essentially this is the whole the forward noising process for your score-based generative model. So the idea is to apply this augmented state space for forward noising, and then somehow reverse this to do a nice smooth backward. So if your forward is smooth, then hopefully the backward will also be smooth. Okay. So what are the reverse dynamics? So essentially, just plug in this extended space UT into your the Anderson equation, or the whatever people like to call it, the reverse SDE formula. So rather than X, you put your UT in and rearrange and input your variables, and you get this kind of SDE here. Okay, so it's actually quite straightforward. So yeah, nothing too like I think it's a good idea, but it's fairly simple to understand. Okay, so how do you actually train this then? So we have here this term, log PT, this grad log PT, it's actually the score term. We replace this with the network here, S UT. So here we have T minus T, which is the reverse time part. Okay. So obviously we don't have access to this noisy UT input, the density of the noisy UT. So how do people typically do this? There's a few ways, like the denoising score matching, where you condition on the data, you simulate forward, and that gives you a close form in expectation. But I'm going to go through another, I guess, fairly standard approach to coming up with an objective for score-based generative modeling, which follows the work from Yang Song, Connor Durkin, on this paper, the maximum likelihood training stuff. Okay, so given some density, P0, so this is like your data density, data distribution, if you like, at time 0, and some other distribution at time 0, Q0. We want to somehow come up with an objective in terms of the score terms here to match your score P0, score for PT. Okay, so this, given the KL divergence, take away the divergence at time T, capital T, and add it again. Use your simple integral. It gives you this form here. So essentially these two terms become, I don't know, the fundamental real calculus type thing. You just plug in your T and 0. Okay, so it's fairly straightforward. Now, how do you attack this first term? How do you do this in a typical approach by Yang Song and people? They first use first note the Fokker-Planck stuff, the Fokker-Planck equation here, rearranged slightly. Then follow through, apply the chain rule essentially. Notice that the H and P, HP and PT, the limit of this will be 0 at when x goes to infinity. I think this makes the integral of the divergence go to 0, I believe. So I guess this is probably like some sort of extension of the divergence theorem or something, but for larger non-complex space. I assume this is what they're doing. They don't really explain it, but it's not.
Isn't it just the density? Yeah, so you bring
the.
Sorry.
No, go ahead. Yeah, what? Sorry, the. Oh, yeah, of course. Yeah, you just yeah, never mind. You just take a derivative of the density.
I'm sure it's some form of the divergence.
Yeah, you can do that as well. Okay, and then yeah, just plug in this this top equation here into here, and you get a nice term in terms of your scores. So this the score term here and the QT here, and so replace this QT with the network, and that gives you an objective essentially for your score. So if you use the network here, you essentially have the final data distribution simulated by using that score. It's close and divergent in KL divergence to the other. Okay. So yeah, how do you apply this to this extended state space? Exactly the same stuff. Replace the xt with ut. You jump through filling in, like the terms become a little bit more complicated, but essentially you follow the steps exactly in the same way. Now the interesting part comes here. So here we have the gradient with respect to ut. And so because the noise is added only to the velocity component and then added simply from the velocity to the data, the argument is that this squared term here, so this transpose times this transpose, only has terms from the gradient of the velocity component involved in it. So this makes things a little simpler, basically. Because you don't have to take the score with respect to the data components. So yeah, that was it's a bit hand wavy, to be honest.
So can you repeat that again?
So I think the idea was, so unfortunately I don't have an equation where I could copy and paste it easily, but the idea is that because the noise is only added to the velocity component, and then the data component evolves from this velocity. That when you take this grad term here, this grad ut, when you, I guess, this term and this term form a square.
The extended space.
Right? Ut is the extended space. Essentially, you don't. There's some cancellation essentially, and you don't have any of the gradient terms with respect to the data. It's just the grad of the velocity term
I
involved.
wonder if it's because of the Hamiltonian kind of thing.
So it's due to the noise matrix. Yeah, has like zeros essentially everywhere apart from the velocity component. So this in this GT in this G here, you essentially have zeros everywhere. So yeah, I think this could be explained a bit better. But why is this interesting? You initialize your velocity at a Gaussian essentially. So this score term should be easier to learn than the score term with respect to data, because essentially it's very close to the score term of a Gaussian distribution throughout the whole trajectory, or close to. And empirically, you can see this if you compare the score term simulated and the actual Gaussian score term at each time point. They're very close. I can show, I'll put up the paper in a second, and I'll show you the plot where they compare the two.
Do you have like an expression for what the backwards drift looks like using the simplification? Now you're saying that the backwards drift sort of simplifies.
Yeah. So you can essentially just plug in this term instead. Right.
Okay. Okay.
So here, so this part will be zero essentially, if that makes sense.
And you're using so the Hamiltonian part is the same, right?
So yeah, it's the same. So it would be essentially exactly the same as the regular score-based stuff, where you take the negative drift and everything like that. Let me find it. So here, I should put I'll jump between the two very quickly. So you see the negative MV XT. You should hopefully see in the previous MV negative XT. Okay. Okay, so that's essentially the main way to derive the score term. But again, you can't really simulate this. So people use so this is the regular score matching loss. If you expand this out, you get this nice term here, and one can use this essentially. Alternatively, rather than using score matching loss, you can use the dot denoising score matching loss, where the expectation is conditioned on time zero. And again, this simplifies to be the score matching plus some extra terms. This is a bit more stable, typically when you condition on time zero. So this is all fairly standard, and it's been done before in the non-augmented state space. Now, what's the interesting part? So another contribution of the paper is essentially coming up with this, I think what they call the hybrid score matching. So instead of denoising towards the data, which is, or the full state space, U0 or X0 in the case of regular score matching, in this augmented space, only denoise conditioned on X0 rather than U0. So not X0, V0, but just X0, and marginalize out the V0 part. And this makes the gradients a bit more stable, basically. So they can show that the variance of the gradients of this estimator is lower than the denoising score matching term. Okay. Which I think, again, is quite nice. What else do they do? So the other, I guess, innovation, if you like, here is how they actually parameterize the neural network itself. Because they noticed that the score term should be close to Gaussian of the noise data. If you look at the Gaussian of the noise data, the Gaussian distribution, and take the score of this, you get something like this, which essentially is essentially it's some Kleski L basically times your Gaussian noise. Okay, and so we want your score network to be close to this. So instead, they parameterize the score network directly as so this alpha theta to be the noise basically. So they scale the neural network output by this this L term essentially. Okay, and that seems to work quite well. Again, this is just hacks. It's just machine learning how to parameterize a neural network, but it actually makes a huge difference. So in previous papers like the Yang Song how to train a training methods or training techniques, they divide your the score output by the standard deviation of the noise data. This is essentially the same idea. Okay, and that's pretty much it really. So now hopefully this makes a bit more sense. So the velocity component again is very noisy. It goes through essentially an OU process, but your data, this x0, goes through a nice smooth trajectory. And interestingly, you can see the image versus the velocity. The velocity looks a lot like the image, and vice versa. Yeah, which is pretty much it. So,
and does it work better?
So in the paper they compare to like the state of the art for Sleve and things. So in this model, in this procedure, they only use 100 million parameters only, and this seems to be so the current state of the art is actually the same or the same lead author for this latent space score-based generative modeling stuff, and they use 500 or 470 million parameters. So that one does a lot better still, but that involves a two-step training procedure where they train an train an encoder decoder, apply the diffusion, and fine-tune the encoder decoder of the data, which is like a bit involved. And I guess they can only really do this because it's NVIDIA and they have millions of GPUs. This is a much simpler, it's a much smaller model for the same number of parameters. This one beats the state of the art. So for 100 million parameters, this is currently the state of the art for generative modeling, but for score-based generative modeling, shall I say. But yeah, bigger models do better, basically. Now that brings
and the velocity starts from Gaussian and ends in Gaussian, right?
Yeah, but a different variance. So the variance will be, of the terminal variance will be a Gaussian, but with the n times by n.
Okay.
I
mean, couldn't you start it at a Gaussian without variance?
Yeah, I guess so. There must be a reason. So let me check. I guess if you want to have this critically damped component, you need to formulate your the SE in a certain way, right? So if we go here, so to get what we want, this needs to be formulated with this M term. If that's not there, then and you start at the noised version, you'll end up somewhere else. So
but that's not the that's not the initialization, though, is it?
No, that's the drift of the
So you could just start at that Gaussian.
But then I guess your drift would be different, right? So so you start at that Gaussian. Oh, I guess you still end up there. Yeah, you'd still end up there if it's you already converged, I suppose. Is that the idea? Even with this new drift, you won't you'll converge to the same target Gaussian.
So that's what I'm thinking. I mean,
yeah, it's not like it will change anything.
If nothing changes, though, shouldn't the score just be? Why is the score not just 0 on the way back? Like
So for the velocity component, so if you start up, where did I put it? So
it won't be, but it's just.
So here is the limit.
It's confusing.
Yeah, so the x goes to Gaussian essentially from data, and your velocity goes to Gaussian but scaled by m. Okay, so this comes from so I'm not sure. The drift isn't as simple as a simple. So this part is the OU process, and then you have the Hamiltonian part xt. So I'm not sure what would happen if you started at the scaled variance term, the initial Gaussian? Would it actually go
But
to?
it doesn't mean, even if you start at Gaussian and you end up at Gaussian, doesn't mean are you gonna be Gaussian throughout?
In this setting, yes. When you condition on time 0, I suppose. So given the depends on the SDE, right? If this is a linear term, then it will be. If it's all affine, I suppose. If it's like a different, if this was more complicated, then it wouldn't be.
Mm-hmm.
So if this was like the log of a different data density that you want to target, then one, you couldn't sample it in closed form, and 2, I don't think it would be Gaussian.
But if it's Gaussian all the way, can you note and like parameterize the score as a Gaussian, and instead of using a neural net, just track the covariance matrix and the mean? Is it just learning a quadratic?
I'm not sure. So wait, so 1 second. The is close to Gaussian, but the score term that you're actually learning is, where is it? This part here, condition on xt, this thing.
Okay.
So it's not exactly Gaussian, but it's close to.
Yeah, okay.
I'll show you the plot. It's at away from time 0, actually, it's very, very close to Gaussian. Because I guess x goes to Gaussian as well. But at time 0, it's you see the difference between Gaussians quite large.
Okay.
So I think this probably answers the question.
Yeah, it's a condition.
So let me find. So they have a nice plot here, which essentially is comparing. So this top one, I think, is correct. It's the difference between the score and the Gaussian that is close to, and you see that the at time zero, there's a large difference for most things. For they call VPSD, the OU process, the regular score-based transfer modeling, and the critically damped stuff. Again, zoomed in, it's not 0, but it's very close to, and it's yeah, and I guess away from time 0, it's very close to Gaussian as well. So I guess what they do is they parameterize this score network. This alpha is not explained extremely well here. Oh, you are sharing? Is it stop sharing or?
Yeah, we can't really see anything. I mean, we can see our navigation bar.
Oh yeah, it says this. I'll share again. You share. Can you see now?
Yes, thanks.
Okay, no worries. Let me find it in the paper. Okay, I'll ignore that for now. So here where they said the score to be scaled by the essentially the standard deviation of your Gaussian plus like the neural network alpha theta. This alpha theta is actually a correction on the Gaussian anyway. So they just put the Gaussian in with whatever drift you want, and then add another neural network instead, which is the actual correction term. And that seems to work quite well. So I think this is nice in many ways because having a smooth trajectory means the neural network you require to learn it can be simpler, which I think is a huge disadvantage of current score-based stuff, that you have to have massive networks.
Why would it be simpler?
I guess because it's just nicer in many ways, I suppose. You don't.
Because like if you're having to like de-log something, you still don't have a noise. Like, are you exploring that volume of the space that
So I guess what you're observing is less noisy, I suppose.
So it's like if you're going to go to
Your trans,
graph,
yeah,
you're still going to have the same level of noise. It's like the trajectory is going to be smoother. But like if you're going to mini batch over time anyway, you're going to be showing random amounts of noise being added. So I'm just wondering, like, is the funnel to the final gathering somehow less difficult?
Yeah, in 1D you can't see it, but like in higher dimensions, that would be the case, I think. You just explore a low-glass space.
This is what you just move the velocity. It's kind of like a different reason why one is better.
yeah, I guess
It's like the critically dampened velocity.
yeah, two different components. Yeah, one, the velocity term is simpler, and two, the smooth trajectory. Because you're not learning the trajectory itself, you're learning the velocity score, right? So that should be simpler, but there is a benefit. I guess when you're sampling, you have less. So there's a problem a lot of people have when they try to do other things with this score-based generative modeling, whereby because it's very noisy, if you want to do a complex, an idea people come up with was using a VAE to generate your the new score terms. This doesn't work because when you apply your forward noising process or your backward noising process, because it's so noisy, essentially you create holes in your VAE's latent space, which means that it's very difficult to train a network to then come up with a score from this noisy version. If that makes sense. So no, this is a different another application which people try to do. These guys actually, it didn't work because of the SD was too noisy.
So like, is this the one where they're doing the diffusion in the latent space or somehow having a VAE to predict?
Yeah, it's not published. It's just another piece of work which never came out, which was essentially they had a problem where they're trying to generate score terms stochastically using a VAE. This then turned up in another paper called this Diffusion GAN paper. But the whole VAE thing didn't work because I think what they thought the reason was is that because the SE was quite noisy, when you try to encode this, you always end up in a weird, you don't end up close to the prior basically. So it's very difficult to train.
So it's like a train test.
Yeah, exactly. Yeah. And again, sorry, it's a bit hand wavy, but essentially they attribute this to the noisy version, the noisy trajectory.
It just seems like there's somehow more space than it's more to that you like train test if I could exacerbate it.
So I guess it still covers the whole state space, right? So it's a convergent Markov chain. It just does it in a smoother way, I suppose.
But it's like if you're covering the whole space, even if you're doing it smooth, like, you know, when you're training, you're going to be sampling from at any point in the trajectory, but like whether it was smooth to get there or not, if it's the same amount of space that
yeah,
then it feels like it would be the same. So I don't really get why like having a smooth trajectory would suggest.
Okay, so in the training part, yes, but in the sampling part, so like you won't get as good, like it would just be harder to train, right? Because in the sampling part where you have an encoder, decoder part, it won't, it will be more difficult. Yeah, I'll try and answer this better. So yeah, I guess you're right. There's two parts. One, the velocity term is close to Gaussian, so it should be easier to learn. And two, having a smoother trajectory. Why is that easier to learn? Or why is it good? Yeah, I'll have a think about why it's a bit better. But yeah, I intuitively to me it seems nicer because it's smoother in the sampling step.
I mean,
or maybe just get better quality samples rather than.
Why are you still covering the same amount of space?
As in, what do you mean by covering the same amount of space? You mean like when you're sampling the Markov chain?
Yeah, I mean, if it's smoother, then it's not going to wiggle as much.
You're not wiggling as much, no, but essentially you still converge. So you're still covering the state space. As in you will eventually cover the state space, it's just in a smoother way. You won't cover it as repeatedly, I suppose, but you will enough to be ergodic.
Yeah, but I mean, your trajectories themselves won't cover as much space. So the thing of the trajectory.
Oh, each individual trajectory.
Yeah, so
Yeah.
you potentially won't have to learn the score on as many points correctly. So with the same number of samples, you're essentially learning the score in a smaller region of space.
Okay. I guess that makes it simpler as well.
Because, for example, you start from your data and you're going to end up at the Gaussian, right? The Gaussian is concentrated as well with your high dimension, whatever. So at the limit where like the thing is.
Oh
super
yeah,
smooth,
I get, yeah. Yeah, so you cover this, you might cover this whole state space, but you won't cover it in the whole, each part of the trajectory.
Yeah.
Yeah, so you'll have a narrower window funnel at each point. That makes sense. Okay, yeah, that makes a lot of sense. Does that answer the question?
It kind of seems like it might be a bit more like mode seeking.
It might be what?
Mode seeking. Like,
yeah, I know
you have a narrow.
you're not covering everything in every part of the trajectory, but you are covering the whole trajectory throughout. You're covering the whole space throughout the whole trajectory. So if you like, you may be narrower at certain points, but you're still covering the whole distribution in aggregate, I guess.
So I mean, take a bridge, right? Take a bridge between 2 points. Take the bridge to be very smooth and take the bridge to be very rough. So if it's very rough, there's a very good chance it's going to cover like pretty much the whole space in between those 2 points. If it's very smooth at the extreme, it's just going to be a straight line. So it's going to be covering much less space. It's not a bridge, but you're starting from a data distribution, you're going towards something concentrated. So
yeah, it's close to, I suppose. I mean, I was look at the trajectories, I suppose. So I guess in many ways the density is in the background. It is more constant. Yeah, I don't think it has a mode issue. It's just.
If you have not many data points compared to how high dimensional your data space is, and you're having very smooth trajectories from that data space, then it seems like you're only really learning your network in very concentrated regions of like a data space. But like if you have a noisier trajectory, then I feel like you'd be exiting these kind of like bridges.
Okay, so yeah, I guess I'm not sure. So you're saying, because I guess the intuition is that if you're adding more noise earlier on or later on, it should be a wider thing. So I think the reason why a lot of these diffusion models seem to be mode covering is that they, I guess they don't train on the data directly. I guess this is still the same reason. I haven't checked the whether they have any results about how mode covering it is or not. But I don't think this should be an issue, because I guess the data will be concentrated anyway at the target. It just often means that your samples won't be very good if it's very noisy close to the target.
does it play a role for the discretization or not?
What, sorry?
Like how noisy it is, or how smooth? Is it easier to discretize?
Oh, I'm not sure what discretization schedule they use, to be honest. I think they did something. Yeah, there is something on there actually about the different schemes to sample from it. I think again, I can't remember exactly. I think the typical all the discretization stuff isn't super stable actually. I think they have a different version.
Okay.
So not the step size, but the actual discretization method. Yeah, I think they use something else. I can't remember exactly what.
They use this kind of symplectic integrator,
Okay.
but they cheat because it's not.
Yeah.
They have a kind of symplectic bit, which is like the standard thing that people use for underdog plancher. It's like Obabo or one of the kind of standard integrator, and then they have a term. They have the score term that they add. So it's a bit.
Yeah, not quite the same.
Why not? I mean, because you destroy all the nice property of the Obabo the moment you have this stuff. So I'm not sure. I mean, it's convenient, but whether it's particularly sensible to do that, I don't know.
Yeah, so they tried it essentially with this probability flow method, this range cutter stuff that people use, and typical standard stuff. So they say it seems to work, but I remember reading the paper and saying that the standard discretization is unstable. So yeah, I don't think. Yeah, I think they use some fancy stuff. Okay. Sorry, a bit of a short presentation. Bit of a last minute one. Cool.